Thanks, Sanjeev. Good morning, everybody. So it's good to be back here. Actually, Christine said that we were she was here with Elmar, but we were here in 2008. Actually, there were 3 teams. I was the team leader of the Speaker ID team. Elmar was team leader of some team which was doing some extensive analysis of how beautiful the voice of Her Majesty Queen is, if I remember it well. And at that time, Christy was a graduate student on the 3rd team. So congratulations to Christy, who upgraded to team leader this time. And maybe we should repeat it in another 8 years.
Next year she will be
So, where do we have my slides actually? Do I need to switch it? Okay, thank you.
Yep.
Okay, great. So the topic of our team is this building a speech recognition system from untranscribed data, as Sanjeev already said before. So what is the problem that we want to be looking at? Then when we train speech recognition system, the standard way of building is that what we have here in this picture. We usually need to collect lots of text data to train language models. We need somebody to give us pronunciation dictionary, so the dictionary that says which word is composed of which acoustic units, phonemes. Then we need lots of transcribed data. We use the transcribed data for training acoustic models, so to train the statistical model that models how different speech sounds works. We eventually can make use of some untranscribed data, which we would use for self-training or some adaptation to some particular domain. So this is what we would do for what we would call resourceful languages, where we have lots of data, lots of transcribed speech available for. And now we would be interested in this problem where we have the language where we eventually have some text. Maybe we can Google out some text related to the language, or we would have some written text for that language. And we have lots of untranscribed speech, and we would still like to build speech recognizer for that. So what our goal here is, we would like to learn from the resourceful languages how we can find some patterns in the text data and in the acoustic data. And we want to learn that from the resourceful languages and then apply this knowledge to the resourceless languages, or the languages where we don't have any transcribed data, and we would like to match the same pattern. So this is the task. How do we match the patterns in text with the patterns seen in the speech? And we would like to learn this knowledge and transfer it to the training the speech recognition system from completely untranscribed data. So how do we want to go about this problem? So the idea here is to use generative models this is the model for which we would consider for generating the speech. Well, these days speech recognition systems are primarily based on discriminative models. Everybody's using neural networks to directly learn how different speech sounds and directly predict if you get these frames of speech or some little portion of speech. Let's try to directly predict which phoneme we are in. Or these days people are really interested in the end-to-end systems where you train some recurrent neural networks for seeing the speech as the input and directly outputting sequences words as the output. So here we want to go a little bit back, and we want to get inspired with the old-fashioned approach where we would be building, again, generative models, perhaps based on hidden Markov models and some generative models of pronunciation modeling and so on. But we want to go Bayesian. So who was here, the students or those of you who are here on Wednesday for my lecture, I was doing some lecture on the basics on Bayesian learning. So it should be we want to go for Bayesian models where we can, first of all, compose the complete model for generating the speech, and also use the Bayesian techniques that should help us to be more robust, should help us not to overtrain. And I will try to give you some ideas on the following slides, just what kind of models we would like to be using. So on this picture, this is the overall scheme of the generative model that we would like to use. Does it? Doesn't? Okay. Can I? Okay. I have nothing to point with, but I will try to point with my finger. That always works. So we want to really start here from. We want to build this generative model where we start from language model. So the language model can be the standard model. We can even assume, we can train it, we can train some Bayesian models for the language model. So but we can start with the standard language model even, so we can have already standard bigram language model trained on lots of text. And this is how we believe that the, good, thanks. This is how we believe that the speech would be generated. So we would start with the language model. We can generate sequences of words, or if we generate sequences of words, we actually can see the sequences of letters. Then possibly there would be some model which is just statistical model that is able to translate letter sequences into phoneme sequences. Then there would be some acoustic model. Once we see the phoneme sequences, we can generate the sequence of speech frames, and that would be the observed output. So this is not much different from what we have been doing, except that we would always have the transcribed data, so we would see the speech, and we would know what is the sequence of acoustic units, and we would directly learn this acoustic model on the transcribed data. Maybe this would be something called, well, here I have it as a letter to phoneme, but it could be also, people often call it grapheme to phoneme. So we would have some pronunciation dictionary. We could learn this component, the pronunciation dictionary. We could learn this component on lots of text data, and then at the end, people would just put all these models together and build the final model of speech recognition. In our case, they will be more difficult because we don't have transcribed data to learn this thing. We don't have the pronunciation dictionaries to learn this component. So instead, we will only assume that this model is known. This is something which is observed, and we will have some generative models which we have no idea what we can't really train them directly. We would just treat these models as some models which we assume certain structure of these models, which would have certain parameters and hyperparameters. So it would be the Bayesian models, and our task would be to really infer parameters or some distribution for the parameters of these models. And these would be Bayesian models that would be controlled by some prior parameters, and we hope that we could learn these prior parameters from the other languages eventually, so we can use the resourceful languages to learn some hyper parameters that would control that would allow us to learn the parameters of these components of these of the language specific parameters for these components, which would be some hidden parameters for us. So just to to show you that we have some idea what models we would like to start with. So for example, for the acoustic model here, so I will now kind of describe the individual components that we would like to plug into our complete model. I would describe them as they were those independent models, but at the end we actually want to plug them into one large model and train the whole model as one single model. So for the generative model, this is something that we have played with and something that people introduced some time ago already. So actually here there is a paper from Jackie Lee and Jim Glass from MIT. They proposed this Dirichlet process mixture of HMM models, and I'm actually just for illustration, I am even showing you on the slides graphical models. So those of you who understand what the graphical models are, I'm not going to explain what exactly the model is about, but I'm just trying to show you that we have the particular idea, and if somebody is interested in, then you can come later and we can even discuss the models and all the latent variables in the model and so on. But just briefly, the acoustic model here, the Dirichlet process of mixture models, it would be a Bayesian generative model where the model itself should, when we train the model, it should jointly figure out what are the acoustic units? So actually it doesn't a priori even know how many acoustic units we have. So it should figure out how many acoustic units, how many phonemes, let's say, we should have. It should learn the parameters of the units, and it should learn what is the segmentation of the speech, and just can learn it on its own. So this model was proposed already before, but in the original version of the model, there was the acoustic units were learned purely just based on the acoustic similarities of segments in the speech. It didn't make any use of looking into structure, like do I see actually some recurring structure of some acoustic events, and so learning some kind of language model on top of these units. So it hasn't been really done before, or to some limited extent. And the original model, there was actually very slow. The inference for the model was based on Gibbs sampling, and it was quite slow. And it didn't make any use of the prior knowledge from other languages. So if we wanted to learn acoustic units for new languages, it didn't try to see what's going on for the resourceful languages, and didn't try to learn anything from that. So this, what we have done already before the workshop was actually Luca Ondel, who is here with us at the workshop. He was playing with re-implementing that stuff using a much faster variation-based training, and he had quite some success, so we can train it much faster. It scales now to much larger data sets, and we already made some initial experiments with actually transferring the knowledge from the other languages. So initially we just did the very simple thing where we try to use the multilingual bottlenecks. So what multilingual bottlenecks is, say you may be familiar with the bottlenecks, the neural network. So it's neural network which is trained just at the input of the neural network you present the speech features, and you try to, at the output of the neural network, you try to predict which phoneme you are in. To make it multilingual, you have actually several sets of outputs for different languages. So you train the whole thing on data from many different languages, and in the middle of the neural network there is a narrow layer that is supposed to encode the important information about the input speech, encode it into some low-dimensional vector, and then try to decode which phoneme in one of the languages you are. And so then what it should do really is to here preserve the important information for phoneme discriminability, but at the same time it should be kind of language independent, because you train it on many different languages. And this is something that we had success with even in speech recognition. So for example, in Babel project, if you start training on these features instead of standard MFCC features, then you already get like 10% absolute improvement just from using these features. Should really learn the relevant information for phoneme discrimination, and therefore it should be actually good for good features for automatically discovering the acoustic units for some new languages. We would have some other ideas about how to actually use how to make use of the other languages and data from other languages, because the model is Bayesian model. So as again, who was here for the lecture on Wednesday should already understand the concept of learning some posterior distribution so the model has some parameters, but our task when we get the data, we learn some posterior distribution over the parameters, so we can learn the posterior distribution on the resourceful languages and use it as a prior for the new language where we don't have any, or we don't have the transcribed data and can limit us in certain way. So there would be different ways of actually doing it, and we can have one example would be that we can originally we can assume that all the languages in the world actually share some pool of phonemes, and then different languages would borrow different phonemes from this pool of these generic phonemes. So we can learn the pool of phonemes from on the resourceful languages, and then when adapting the model to the specific language, it can pick up the phonemes from the pool of the phonemes. If there is need for yet another phoneme, it can actually learn, okay, I'm missing something, so I can learn new model for completely new phoneme. The model is able to do that. And even for the phonemes that we find there would be similar phonemes from the other languages, it can actually adapt it and get some more more specific variant of that phoneme. So this model should be really able to make use of data from other languages. There was another thing that we were considering, and let's see if we get to that during the workshop, would be using some structures like what we worked on here on 2009, actually, with Denpo with the subspace Gaussian mixture models, which is another model where here the acoustic units would be modeled by kind of standard HMMs except that the HMM states are just described with very low dimensional vectors, which would be like phoneme and language specific low dimensional vectors, and these vectors are then together with some larger matrices of parameters which are shared across different, so there are some parameters which are shared across phonemes and across languages, and those could be again learned from data from all kinds of languages, and then we could just learn the specific parameters for the new language. So we can use this strategy also in our case. Okay, so so far, what I was talking about was just the acoustic model. So now so there would be just this component of the model, but we have some idea also about the letter to phoneme or grapheme to phoneme component. And actually, there are several variants, but one of those that we are looking at right now would be again from some model that was introduced at MIT, which would be based on hierarchical Dirichlet distributions and something that is able to model. So again, Bayesian generative model, which is useful for modeling pronunciation lexicon, and it can also account for the context dependency in the model. So it can actually model something like triphones that we would have in standard speech recognition systems. So another kind of generative model that we would like to consider and plug into our system. And we are lucky to have people on our team which were previously working on automatic word discovery. So there would be models making use of nested pet-manure language models, and so this is another Bayesian model. This is actually another Bayesian language model which is useful for automatically segmenting. Automatic segmentation. So I took from Daichi, who is here with us, some example from his paper, which I guess demonstrated quite well. So this is the excerpt from the Alice. What's the English name? Alice in Wonderland book. So here, this is basically excerpt from the book by dropping all the spaces, and this is what the model can do on its own. So it just sees the text like this, but the model is designed in such a way that it should prefer it should try to search for some reoccurring sequences of words and learns even n-gram language model on these reoccurring sequences of letters. And at the end, so the idea of the model is, okay, this in speech, we actually have some language model put on top of the word. So there are reoccurring sequences of words, and they have certain pattern, and each word is composed of letters, and we can build also some language model on top of letters, which tells us how words would be built of letters. And let's put these things together. Let's train the model, and if we figure out what the sequences of letters what would be for different words and what the language model for the word would be, then the model at the end is able to give us something like this, which is actually automatically learns how to segment the original speech into original letter sequences into words, and segment the words, put the spaces at the right places. So we want to also be using similar kind of models, except that instead of the letter sequences, we would be using phoneme lattices or lattices of the automatically discovered units, or actually we want to plug this model directly to our big scheme, so we don't even know what at the same time it should discover the acoustic units, and at the same time it should do the segmentation, at the same time it should discover what the language model on top of the word is, and things should be then joined and trained. So there was I selected here the two papers, one is from Daichi, which was the original paper on the nested pit-manure processes, and this is paper from the guys from Paderborn University that we have also on our team, which already extended it to processing phoneme strings, phoneme lattices, something in the directions that we want to continue on during the here at the workshop. So. During the planning meeting last fall, the WS asked to concentrate on center criteria, why people should, I mean, people that were voting for the proposal were supposed to consider this criteria. So I actually made the slides on the criteria, and then I figured out that this actually, even these slides nicely summarize what we want to do for the workshop. So one of the criteria why people should have been voting for our proposal was the scientific merit. And here, what we say is that we really want to build on recently proposed Bayesian models, but now we want to make non-trivial extension of the model and non-trivial combinations of the model to achieve some new goals. So there would be the models that I was just talking about, the Dirichlet process mixture model, infinite mixture of HMMs is how it's also called, the different models for the hierarchical Dirichlet distribution or hierarchical Pitt-Manure distributions for modeling the G2P components, or just what I've mentioned, the nested Pitt-Manure models for the automatic segmentation. So we would like to make use of these models and combine them together and extend them in the way to achieve our goals. Potential impact of this project. Well, there was actually recently quite high interest in processing speech from lower zero resource languages. So just as examples, these doesn't work anymore. Okay, DARPA Lorelei project or IARPA Babel project would be two projects that are really dealing with such cases. That DARPA Lorelei is just the most recent project which should be the project about disaster relief. So when some agency or let's say even U.S. Army comes to a place where just some natural disaster stroke recently, then they would like to process the data and they would like to really direct their efforts to the right places, and so they would like to collect some data from SMS messages, data from news, data from telephone calls and so on, and they would just like to make some sense of it, but it can be language that is not really, well, hopefully it would have written form, maybe doesn't even have written form, but even if it has written form, there may not be any speech recognition system available for it, and they would like to start processing the data immediately. So if we manage to create speech recognition system out of the nothing, out of just the untranscribed data and text, we should be able to provide at least some information and maybe pass the transcribed speech to the NLP people and let them do whatever they know to make some sense of it. So what we want to work on can be also useful for keyword spotting and keyword spotting for the languages, again, where we have no transcribed data, so maybe even things like query by example, but especially the keyword spotting where you just really want to search in the audio data for a language where no speech recognition system was available. So actually our model can directly, once we do the inference in our model, it should take the training data, and as a result of the training data, the output should be really segmenting the speech into words, saying which words we have in our vocabulary, and saying what are the sentences in different utterances. So it should actually provide several pieces of information: the language model, the dictionary, pronunciation dictionary, the transcription itself, and so on. One of the things that we really want to concentrate here is to make it scalable, to be able to build models that would be applicable to large data sets. And well, we hope that we will achieve something and that we would have tools that we will be happy to share with we would like to just make them public. One of the criteria was, is it really feasible? Well, we say we are actually building on models that we already have available. We have already done some work. We already try to scale the algorithm so that they can be run on larger amounts of data. Now we just need to combine the models and see if it all works together. And I have the team on the next slide, so that's actually related to the feasibility, but let's wait for that. Well, novelty, I guess that I already said most of it. This is something that hasn't been done before, building really this training speech recognizer on untranscribed data. They were not really, I think that this is really the first attempt that we try to achieve the whole thing, just training the full speech recognizer on completely untranscribed data. Well, I hope that we will achieve something. I guess that it will be something quite suboptimal, but hopefully it will serve as a starting point for some ongoing research where people will try to solve the problem with simpler and more effective techniques, but hopefully this will be something that would start this effort. Just on this slide, I have the list of the people that we would have on the workshop. I just listed some of mostly just the senior researchers, but you can see their expertise. So we actually really brought people that have expertise in different things. In Brno, we would do mostly the speech recognition and using the low resource languages or the acoustic modeling. There would be people which are expert for the Bayesian language models and automatic word segmentation and so on. So I guess that we have pretty good team of people and that have different expertise, and that we would be able to put all these pieces of information together and build the final system. There are actually few strategies that we would like to concentrate on. So I just described the kind of one of the goals, building the speech recognition system from untranscribed data, but there would be different strategies that we can take, and I just briefly describe those. We can build system where we wouldn't really have even the language model, so they would be based on the automatic. So one of the models that I already tried to describe, something where we have just the untranscribed speech. We don't even have any language model, but using the models for automatic word segmentations, we can actually figure out what the acoustic units are, what the phonemes are, and how the words are composed out of the phonemes. So here we wouldn't be able to transcribe speech in letters, but we would at least be able to figure out that there are some acoustic units in the speech which are actually words, and that could be used for query by example, or someone could review the most frequent segments of speech that are identified as words. Could be already useful for different applications. Or another strategy that we can take would be, well, the full thing where we start from the language model, but we can still distinguish two different scenarios. The one is that we have words we have language which is actually alphabetic language. So when we have the trained language model, we have words and we know which letters different words are composed of, and then we can have the component which is the G2P component, and we can land in the pronunciation dictionary, but we can even consider less constrained scenario where where the language model could be it could be language which is not even alphabetic language. So in that case, we won't have the letter to phoneme component, but we would again have to make use of model similar like in the first case, where it would learn lexicon, but only lexicon in the sense saying, okay, this Chinese character is this sequence of our acoustic units. So it would still be able to transcribe speech from the audio to words, but we wouldn't have the luxury of taking use of the additional information that words are actually composed of specific letters. We would just need to learn that word number 1 is actually the sequence of acoustic units and so on. So we would like to look at all these strategies during the workshop. This just briefly describes the data that we want to work with. So there would be perhaps working with trying things on Wall Street Journal, and we would like to make use of some of global phone databases as the resourceful languages, and perhaps on the spontaneous Japanese corpus, and we need to also make use of DARPA low relay data as as our team is also sponsored from this project. I guess I'm running out of time, and I've spoken about all the other things. How we would like to measure our success? Well, we can actually look at different things. We can look at how good we did in terms of just automatic units discovery, and we can use different metrics like normalized cross entropy between the discovered acoustic units and true phoneme strings. We can try to, if we just automatically discover the acoustic unit, we can be testing on different tasks like phonotactic language ID, or use it in language ID systems, query by example, keyword spotting. But the ultimate goal really would be to build the final end-to-end unsupervised ASR system and measure the word error rate, how well we can actually transcribe the speech. And well, that is it. So thank you.
You have the additional knowledge of phonetics books that characterize languages already, or would you not?
So, can you be more specific? So what would be the...
Well, many languages are described already
So,
by phoneticians, or
well, no, we don't want to use that eventually. I mean, the models should be extendable in this sense. So when I say that we want to really build the end-to-end ASR starting from language model, just seeing the language model, or maybe just seeing the text and then seeing untranscribed data, maybe this is the most ambitious goal that we would like to achieve. But of course, there would be if it is alphabetic language, then we know the letter sequence for each word, and we can use that thing. We can use it blindly again, and we can hope that the lexicon component will learn how letters transduces or translate into phonetic sequences. But if we have some small pronunciation dictionary, maybe we can initialize this model with it, and we can just at least use it as the initial guess. And so if we use that, then we would already say, well, we actually already know what phonemes are in the language. But maybe this is fine. We can even use it as an initialization for that language, because we also hope that this component wouldn't just learn what phonemes are in the language, but maybe what triphones are in the language, and even learn the context dependency. So we can always use it as initialization for the model, and then we can run the inference on the whole model, and maybe it will learn yet something else. So we could eventually use some additional information that comes from some linguist expert. Maybe we would have just a very small pronunciation dictionary. Maybe we would have very small amount of transcribed data, and maybe it would be even transcribed in some loosey way, and we can use it somehow. We can use it as some initialization for the model, and eventually it will learn more on its own. So, and we actually think that we will have to use some of such tricks to initialize things well. And
my expectation would have been that, the IPA was developed to describe exotic languages, so it would be probably easier to have a description of phonetics and not have transliterated data. Many languages don't have a transliteration.
Also, most of the zero resource or low resource languages would be alphabetic, because most of those would be, well, maybe that would be my guess, at least, because most of the languages that didn't have written form, and where the written form was developed just recently, it would be derived from some alphabet already, and they would be usually quite phonetic. So the hope is also that if we actually know what letters the words are composed of, it should be already quite some supervision for the whole training process. So maybe it wouldn't be that difficult to infer the lexicon. But we actually want to start with English, so we want to even make our lives more complicated. Yes.
The root hash to my sense is that you still hope that you will discover for these and words, or are you open to discovering something else?
So they are the.
How much of your approach is biased to what you already know? And
Well,
how much you are open to maybe, going there
We don't-
to the wilderness?
Yeah, we don't think that it would. Still, the generative model is kind of based at the moment and the assumption of the generative process that our old-fashioned speech recognition system made. So it still assumes that the words are composed of some acoustic units, not necessarily phonemes, but there could be the statistical model that says if I see this letter of this sequence of letters, it translates into this letter of some acoustic units. No idea whether those should be phonemes or not. But would be sequence of acoustic units, and then this sequence of acoustic unit translates into sequence of speech range.
I'm a little confused as to how it knows it is at the word level, as opposed to syllable or morphological unit or phonosyntactic. I mean, there seem a lot of different levels of language in the generative model. What pushes the word levels?
Because we don't have much text transcribed in terms of syllable units. I mean, usually,
You're putting the word demarcation as part of the model.
because what we assume that we would have at the beginning would be just the text and the untranscribed speech data. This is what we have. So if we believe that there should be something, we should do some modeling on the syllable level or anything like that, then we should build it in terms of another statistical model that translates the sequence of letter into syllable-like units and so on. But at the moment, we hope that it would be done by the lexicon itself, because the lexicon would have actually some kind of structure that can hierarchical structure that can learn what the n-grams over letters are and some structure over that, so it can learn something like syllable structure in the model.
So in the kind of scenarios you were describing where you have some text and you have some speech, you may not have the speech transcribed, but oftentimes you know what the speech is about. Right? So based on that, you might be able to sort of say with high confidence that certain things must be in it. Like, maybe you have high confidence on the subset of the vocabulary, saying, I'm sure these words are being used in this speech. Are there hooks in the model somewhere where you can say, okay, I do want to do automatic word discovery, but I expect that these words, or some of these words will be there? And how do you get that kind of knowledge into this model?
I think it's kind of like a language model, because if you want to make it work, then your language model should be able should match actually the type of speech you have in the audio. So I think basically if the speech is an audio document about some earthquake, then the language model should be actually reflect people talking about earthquake or situation of panic. And then like this kind of knowledge, I assume it already in the language model.
The supervision that you have for the untranscribed speech is basically the language model. So you could always adapt the language model or use more specific language model for that given sentence that would favor certain words. So it would be about adapting the language model, or even.
I'm thinking more of adapting in the sense that the text might be very generic, but I might have additional information about this piece of speech. So, for example, maybe the speech comes with some metadata. And the metadata would be words in the language.
But then,
using those words, you could key off and get other words. In other words, I might have reason to believe that the generic language model is not a good fit for this data. So how do you break that?
but then we are perhaps talking about yet another project, which is adaptation of language model to specific topic and so on. And yes, we are open to any language model. Even Taka is working on the Pitman-Yor process-based language models, and it could eventually use some other latent variables that would be describing the topic, and we could feed it in some additional information. But I guess that this is really already, we are talking about yet another project, which is just how do we adapt the language model. But we could at least get inspired by that thing, and we could actually have because we really want to do, when we initialize our model, we think of using all kinds of Oracle initialization. So like if we have this letter to phoneme components, we can actually train it on huge lexicon and get the ideal pronunciation dictionary. We could even have the language models that would be perhaps adapted to each specific sentence or each specific subset of the data to get something Oracle and start with that, and hopefully this Oracle initialized. We can Oracle initialize the whole model in such a way that it actually has to get things right, and then we can run the inference and see whether it at least stays as good or whether it degrades, and tune the parameters based on that. So this could be one of the things that we could consider as doing some cheating experiments, see how much better we could do if we get adapted model and we know really what words are in this particular sentence or something like that.
Yeah, the direction I was thinking of a suggestion to look into is the observed variables should not be just the speech, but the speech plus any metadata that goes with it. It says that this speech is about these things, or this speech was recorded under these conditions, and so on and so forth. In that way, and that hook may not be to these subword units. It might be all the way back to the words.
Yeah, that is okay. Yes.
So following up on what Sanjay was just saying, when you're transferring over knowledge from a different language, you're also going to have a problem with channel differences.
Of course. Yep.
Do you have any thoughts on how you'll sort of distinguish between those?
Well, the thing is, so one of the things that we started using would be the bottleneck features, and they actually, once you start training them on all kinds of different channels, they actually becomes quite robust. So and then just by learning how the phoneme how to discriminate between phonemes for different languages, and each language having recorded over different channels, that actually to some extent takes care of it. So yes, there would be the problem of eventually figuring out what is the channel variability and what is the phonetic variability. So one way of dealing with it would be already these bottleneck neural networks that we want to consider. When I was talking about these GMM models, where you actually model the subspace with here I would have we just model the subspace of phonetic variability, but we could even do things like what we did in Speaker ID, where we have subspace with phonetic variability and channel variability, and we could actually elaborate on at this level and try to decouple the phonetic variability from the channel variability and do adaptations that which actually was even in the full SGMM model. So we could do something like that. I don't know whether we really want to go all that way during this workshop, because I think that we have the first goal would be just to stitch all these different models all together, and then we can start elaborating on the different components and solving these different problems. I think that at the moment the multilingual bottleneck features are quite good solution to this problem. Yes. No, there wouldn't be automatic words. We would even what actually Takahiro does, he even tries to learn the language. He would use Pitman-Yor process, hierarchical Pitman-Yor process for learning the language model, and he could actually discover new words that didn't exist in the training data, and then can create some problems. But in the simple case, we would have the fixed language model. We can even assume that there is a fixed vocabulary. So if we have enough of text data, we can assume that the vocabulary is fixed. We know what the words are. We just don't know where they are in the untranscribed speech. So then we can just do the normal thing, just transcribe it with the word that you believe that are in the vocabulary. And of course, there would be some OOs, and you will get some error because of that, but they may not be that high.
More questions? It's time to crush again.